How'd I do on my derivative? Little quotient rule, derivative the top, leave the bottom alone, minus top, derivative the bottom. All over the bottom squared. So I think if we clean up the top, this actually just works out to be 4 over x plus 4 whole thing squared. I mean 20. I don't mean 4. And by 4, I mean 20. Because those 5 x's are going to cancel out. So that tells me I already know some things. This does not have any relative extrema. There are no values where my derivative is equal to 0. There is, however, a place where my derivative is undefined. So if the question is asking me about critical numbers, meaning places where it's equal to 0 or undefined, that only critical number that I'm looking at is x equals -4. Which makes my derivative undefined. By the way, it also makes my function undefined. I already knew there was going to be a vertical asymptote at -4, just using our skills from section 3.6. I think I'm right on that section. But I still care about where we're increasing and decreasing. So I might still think about a number line, but don't think too hard, because no matter what I plug into the bottom, I'm about to square it. Which means no matter what else is happening, this thing is always increasing. So if I were to draw a number line for this derivative, the only thing going on, it would be -4, but I'd be positive on both sides. So in terms of intervals where we're increasing, we're going to be increasing from -infinity to -4 and from -4 to +infinity. And we're decreasing nowhere. Now, as a web work question, we would have to read the question to see how we're supposed to put the answer in. The weirdest way I've ever seen to have to put the answer in is empty squiggly brackets. So if you are struggling and you think you've got the right answer in web work and you've tried all the other things, try empty squiggly brackets. Technically, we refer to this as the empty set, meaning there are no values where it's decreasing. That's really a notation thing. I would never write that on a test. On a test, I'd write it's decreasing nowhere. I would just write it out in words. But as a web work thing, if you need something to try, squiggly brackets with nothing inside. Now, if we're going to classify any relative extrema, there are no places where my derivative is equal to 0. So there are no relative extrema. There are no relative maxes. And there are no relative mins. And just for fun, let's think about what this graph actually looks like, because we have those skills. We have those skills from midterm 1 to be able to figure out where the vertical and horizontal asymptotes are for this thing. So just for fun, we'll do a quick sketch. So if I'm looking for vertical asymptotes, I'd be looking for values that make the denominator equal to 0. So that's that -4. Horizontal asymptotes, I know technically I'd be taking the limit as x approaches infinity. And then I'd find that largest power of x in the denominator, divide everything by that. And I'm looking at a horizontal asymptote of 5. I also happen to know that I've got intercepts at 0, 0, because if I plug in 0 for x, my y value would be 0. And that's enough for me to graph this thing. So I've got intercepts at 0, 0. The horizontal asymptote up here at y equals 5. A vertical asymptote over here at x equals -4. And on top of that, I know that this function has to be increasing everywhere. So it should be increasing over here and increasing over here. Yeah. Oh yeah, so I was using my skills from before. So if I look at the limit as x approaches infinity, and I go back to where it started, the 5x over x plus 4, largest power of x in the denominator is just the x. So I'm going to divide each term by that largest power. By the way, the book also tells us that we can just look at the largest powers of x. But if I divide by the largest powers of x, I'm going to get to this limit. Those x's cancel, that turns into a 1. And then 4 divided by a bajillion goes to 0. So this kind of turns into 5 over 1 plus 0. Yep, no problem. Now let's say that I'm looking at this graph. From the graph, I know what the number line for my second derivative should look like. Because I know that over here, my graph is concave up. And I know that over here, my graph is concave down. Which I've always thought was kind of cool, that if you're good at graphing, you kind of know what your number lines are going to look like. And if you're not good at graphing, that's okay, because you can use the number line, right? So 2 different tools to get to the same place. Just to confirm that this is what we would get, if I take a look at finding the second derivative of this, by the way, I probably would not do that as a quotient rule, though there's nothing wrong with treating it as a quotient rule. But if I had to take a second derivative of this, because there's not much going on top, I would choose to think about that as 20 times x plus 4 to the -2. So that when I took my second derivative, I'd have -40 times x plus 4 to the -3. And then if you wanted, you could rewrite that to be -40 over x plus 4 cubed. There's the -4 for where our second derivative is undefined. Awesome. And if I pick something bigger than -4, like 0 to plug in, for sure that's negative, which matches our graph. If I pick something less than -4, like -5, plug that in and my bottom's going to be negative. Negative over negative will make that positive. Cool, matches our graph.